Welcome to section 5.4, and this section is titled Optimization. And all it's going to mean to us is we are going to learn a process to maximize or minimize desired values. And so places where we can see this would be things like an economic situation, wanting to maximize profit, minimize costs, in buildings and architecture, wanting to maximize efficiency, which could be maximizing a space based on a certain amount of materials. This is the first true lesson where you're going to be applying previous skills. I can give you a general list of strategies for working with problems that involve optimization, and then we'll get into what those problems actually look like and what is going to tell you that you are trying to optimize some value. Step one, and a very important strategy, is to draw a picture if there is a visual that we can create. And we're also going to identify any known and unknown quantities. After that, optimization requires us to write an equation or a model. And here's the big step. Whatever equation you are trying to optimize, we have to get it in terms of a single variable. We will learn something in the upcoming section that allows us to work with derivatives when we have multiple variables, but the math is much easier if we can get one equation, one quantity in terms of a single variable. And where the application of our skills comes in is that all optimization is talking about is finding a max or a min. And this can be relative or absolute. It depends on the problem. And so again, that's why these are general strategies. And that's why you'll even see step 5, which isn't always going to pop up, is we're going to want to determine the domain for our problem to see if our max or min might occur at an endpoint for the problem. And so if these strategies don't make a lot of sense just yet, that's because we haven't tried to put them into play. So let's scroll over to example 1. And example 1 says, find two numbers whose sum is 30 and whose product is as large as possible. So the big thing is step 1, and it'll kind of be doing steps 1 and 2 you saw from the strategies together. I want to really identify this as an optimization problem. And I do that by noticing they're asking me to find a product that is as large as possible. Let's change that into something that means a little bit more to us. Maximum of a product. And we can work with finding a maximum or a minimum if we have a function to describe this value. And so there's not really any picture we can draw. The best we can do with our picture is really to write an equation that would show this. And so a product we'll call P is any two numbers multiplied together. Let's call those X and Y. And in terms of known and unknown quantities, well, I know X is just, we'll call it the first number. Y is the second number, and we also know from the problem the sum of these two numbers is 30. And there's everything we currently have. So the second thing I'm going to think about is that quantity that I want to optimize. Is it in terms of one variable? And if I look back up, nope, there's an X and a Y in there. That's a no, and that's something we're going to fix. And how we're going to do that is, well, I can't work with both X and Y, but if I could get one in terms of the other, this would be okay. I'm going to draw on this piece of information right here, remembering that X plus Y do have a relationship. This is something that relates X and Y. And I can solve for either one. Let's go ahead and solve for X. X would be equal to 30 minus Y. I now have X in terms of Y. And I'm going to substitute that back into my product equation. My product will now read 30 minus Y times Y, and I can distribute that to get 30Y minus Y squared. And when I answered no before about being in terms of one variable, I can change that to say yes, and I can move on to the next step. And the next step will be to use calculus to find where my maximum is located. And here's the step where we optimize our function. And how we do that, back from 5.2, first derivative test, we're going to take the derivative of our product function. And we'll just go ahead and call that P prime. The other thing we could also call it dp over dy because we are differentiating this p function with respect to y. And it will be 30 minus 2y. And then remembering how we find max or min, we're going to think about our two cases, where p prime equals 0, where it doesn't exist. Does not exist, it's polynomial, so that's none. And for the other, we're setting this equal to 0. And we'd end up with a y equal to 15. And the last step is really the rest of the analysis to figure out, is this the spot where my maximum is going to be located? So first thing we're going to think about is the domain for that function. And what you got to think about, it's a product of any two numbers, so your domain is going to be all real numbers. Why this is an important thing to think about is if you have a restricted domain and multiple critical values from step 3, you might be able to knock some of those values out as possibilities if they're outside your domain. So we're going to open ours up, and we'll set up our sign chart with 15. This is our p prime sign chart, and we can use test values, say 14 and 16, and test those out in p prime. If you were to plug a 14 into p prime, hopefully we can see we would get positive values. Plugging 16 in would give negatives, and without endpoints for this domain, this location where p prime changes from positive to negative has to be where our only maximum is located. So we have a maximum when y equals 15 because p prime changes from positive to negative. And so our two numbers, y is 15, x will be 30 minus y, 30 minus 15. It's actually going to be the same exact value. So the two numbers that we wanted were 15 and 15. And that maximum product we would get would be the product of the two, in case that were a follow-up question that you could be asked. Moving on to example 2. Notice we have a graph of y equals square root of x, and we want to find what point on this graph, on this curve, is closest to the point 5, 0. Point closest has to tell us that what we are trying to do is minimize a distance between 2 points. And I can warn you that some of these problems are going to require you to remember some formulas from geometry and algebra classes. This one, what we're going to have to think about is we have a known point, 5, 0, and we have an unknown point, x, y, that we can put anywhere. And we're trying to figure out this distance. We're going to just take advantage of this graph and make that our picture. But beyond that, we actually know that the second point is not just x, y, it's x, square root of x, because all of our y values are defined by the square root of x on that curve. So what we want to do is make an equation that's going to define this distance. And what we have to remember is our distance formula. I'm going to write the general one just so we can make an extra note about it. It's square root of x2 minus x1 squared plus y2 minus y1 squared. And putting in everything we know about that, we're going to have our second x value, the unknown one, minus the known one, 5, plus our unknown y value, which is actually square root of x, minus 0, our known y value. And we can simplify this down a few more steps. I'm going to expand this out, and we'll get our distance will be defined as square root of x squared minus 9x plus 25. And remember that question we got to ask ourselves. Is this all in terms of one variable? Well, because we linked y as being square root of x, yes, we do have this in terms of one variable. So we'll move on, and let's go ahead and optimize. So we're going to take the derivative of our function and have to apply the chain rule. And we'll get d prime equals 1/2 x squared minus 9x plus 25 to the negative 1/2, and all multiplied by the quantity 2x minus 9. And just like we did with first derivative test, second derivative, let's get this into something that makes more sense. That 2x minus 9 can move into the numerator. We'll have a 2, and we'll change this back to a square root. in the denominator. So that now we can go ahead and break down our critical values. So the d prime equal to 0 case, remember for that, isolate the numerator, and we'll get x equals 9 over 2 or 4.5. The d prime does not exist. Well, that's going to be where x squared minus 9x plus 25 equals 0. I'm going to tell you that's going to be none. You'll see pretty quickly factoring won't work. If you try the quadratic formula out of this, when you get to the discriminant, the b squared minus 4ac, that's going to end up with a negative value. And trying to do the square root of a negative will give you only imaginary solutions, so we're not worried about the does not exist case. And so we'll hop back down here and finish our analysis. The big thing when we start the analysis, pay attention to the domain for your input variable, in this case our input variable x, and notice back on the original function, we were dealing with y equals square root of x. That automatically locks down our domain to be all x values greater than or equal to 0. Luckily we had one of those, nice positive 4.5, so we're going to start our sign chart at 0, include a 4.5, but let it go to positive infinity when we take a look at d prime. And the cool part, when we test out our values in this fraction, recognize that this denominator is always going to be positive because we're taking positive square roots, so we're really just breaking down if this is positive or negative. So if we use something like 4 or 5, using a 4 would give us negatives, 5 would give us positives, and so our relative min, which is nice because we wanted to minimize this distance, at x equals 4.5, and we can finish our problem by answering the original prompt. The closest point is 4.5, comma, and remember, y values were determined by the square root of x, and we're just going to put square root of 4.5 and not worry about doing anything else with that. And so one last example before I set you off into the world to try to apply calculus to other situations. I'm going to need to make an open top box. So just realize that's box, no lid on it, to store all my Pokemon cards. I have a piece of cardboard that is 14 by 30 inches. Right away, I'm not even going to mess around with steps on this. Once I see that, I'm going to immediately make the picture. So I've got this piece of cardboard that is 14 by 30. Now, in order to make this into a box, what I'm going to do is I'm going to cut squares of equal size from the four corners so that I could fold four sides up and turn this into a box. And hopefully you'll be able to visualize that. What I'm going to do is I'm going to take a pair of scissors, cut the same exact square off each corner so I can make this into a nice rectangular box. Problem is, I don't know what size the squares need to be. I'm cutting off some x by x square at each corner, and I want to create a box with the largest possible volume. And now we can get into breaking down the strategies we talked about for optimization. The reason I know I'm dealing with optimization is that last phrase has to tell me I want a maximum volume. And so we've already set up the picture, but we have to realize that when we fold this to make a box, which could look something like this, but with no lid, the volume of that shape would be length times width times height. The problem with this is that it is definitely not one variable. But think about it, everything's coming down to the size of the squares I'm cutting out. So what I can think about, especially if looking at the diagram, let's call length the 30-inch side of the cardboard. And the actual length of my box, when I take these squares away and fold it up, this actual length right here is going to be 30 minus the x that I cut off from either side. So 30 minus 2x. Similarly, the width would be 14 minus 2x. And the height, when I fold these sides up, is going to be completely determined by the squares that I cut out. The height's going to be x. And so I can rewrite my volume as length times width times height, and expanding that out and rearranging some things, we are going to get 4x cubed minus 88x squared plus 420x. And now we're ready to optimize. Here we're going for the change in our volume with respect to that x variable, size of the square we're cutting off. Also, we can call that v prime. It will be 12x squared minus 176x plus 420. I'm not even going to pretend that we have to worry about the does not exist case here because it's a polynomial, so we're just going to focus on setting this equal to 0. Going for a greatest common factor first, that greatest common factor will be 4 to give us 3x squared minus 44x plus 105. Big one to factor, but hopefully we can get there. This will become 3x minus 35 times x minus 3. We've got to be comfortable on our factoring skills. And setting each of those equal to 0, the first one would be at 35 over 3, or 11.667. And the second would be at x equals 3. And we can jump into our analysis. One thing to realize is your domain restriction on that x, on what you can cut off, the smallest amount that you can cut off would be 0. You don't make any changes to this, and you just have a piece of cardboard that you're laying Pokemon cards on. But the most you could take off would have to be 7. If you think about this short side with the 14, if you cut in 7 inches on both sides, you would have actually cut all the way across the piece of cardboard. We can't do any more than that. Since we can only take values of x that are between 0 and 7, the 3 is the only number we can use, and we can get rid of this 11.667. And we can build our sign chart to go from 0 to 7 for v prime with a critical value at 3. And you can test values like 1 and 4. Remember, go the efficient way, test those in the factored form, and you will end up getting positives over here, negatives over here, which is what we want to see. And so we will have a maximum when x equals 3. This one does have 2 endpoints, so you might worry about an absolute max being elsewhere, but the absolute max also at x equals 3, because this thing only increased and then decreased, it never increased again. This has to be my absolute highest point for my original function. And so the answer of what size squares we should cut off 3 by 3 squares. And that does it. Like I said, this is a process. It's a way to apply previous skills. It's not an exact skill, so I can't show you every possible scenario you might encounter. You have to be on the lookout for words that let you know you're dealing with trying to find a maximum or a minimum, set up a function in terms of one variable, and then you're running the same analysis that we did using the first derivative to find relative extrema. It's going to take a little bit of work at first, but please go ahead, start practicing as much as you can. Make sure that you review and summarize these notes, especially the process for dealing with optimization problems, and thank you for watching.